So we have now timed the blinds. They take 22 seconds to come down. So future colloquia will try to arrange it that they get to the bottom at 4 o'clock exactly. So this is an annual event of some importance in our calendar. It's the colloquium in honor and recognition of Cecilia Payne-Gaposchkin, who played a very significant role in the development of the understanding of stellar spectra, and particularly the importance of what was then the very new quantum and statistical mechanics in their applications to stellar spectra. And we actually have a very good speaker today in Bruce Draine, who's... yes. Did that not come out right? Let me start again. We are fortunate to have a very good speaker today in Professor Bruce Draine from Princeton University. Bruce was educated at Swarthmore and at Cornell. But between Swarthmore and Cornell, he spent a couple of years as an educator in the Peace Corps in Ghana, if I remember right.
Yes.
Yes. He postdoced here and at the Institute for Advanced Study and joined the Princeton University Department of Astronomy at Peyton Hall in 1982. Bruce has worked on a wide range of interesting problems in the interstellar medium. And I think what's striking about his approach is that his very solid approach, starting in basic physics, a deep understanding of physics and its application to the substances that might actually be found in the interstellar medium. And a very significant improvement in our understanding of those physical processes and their consequences for what we might actually observe. And that's characterized his career. It's led to a significant book on the physics of the interstellar medium. And it's what we're going to hear about today. And where is your title? Andromeda's Dust. So with that, I think it's important that I get out of the way as soon as possible now. But I do have one more responsibility. Is that there was a symposium on the history of Cecilia Payne-Gaposchkin, and it led to the production of this book, which we're happy to present to you with our thanks for visiting us.
Well, thank you very much, Charles.
Thank you. Bruce Draine.
Well, thank you for the very kind introduction and for the invitation to speak here. And I'm really honored to be able to give a lecture named after Cecilia Payne-Gaposchkin, who was truly a preeminent scientist of the 20th century. So what I'm going to tell you about today would not have been very close to her heart. She was interested in stars and understanding, in particular, stellar atmospheres and novae and so on. But of course, dust does get in the way, and so she surely was familiar with the problems that were posed by dust. Shortly, towards the end of her career, we were learning through infrared astronomy that stars actually produce dust, so that would have been something that she was aware of. We didn't know very much about it at that time, and we didn't know a lot about the inventory of dust in the galaxy, but we've come a long way since then, and infrared astronomy has actually been a key part of leading us through this. So I'm a theorist, and I like to approach things theoretically, but I'm be the first person to concede that what we know about dust has really, in almost all cases, we've been led by observations which we then try to understand, going from the very discovery of dust as something obscuring parts of the galaxy. Herschel didn't understand what he was seeing when he saw dark areas in the sky, but eventually astronomers figured out that it was consistent with obscuration by particulate matter, and then we've come a long way since then by being able to study that at many wavelengths. Now today I'm not going to try to talk about where we stand in our understanding of dust. I'm simply going to try to take our study to the Andromeda galaxy and see what we can learn about the distribution of dust within Andromeda, the quantity of dust that seems to be present, and the characteristics of the dust that we see there, whether it seems to be of a uniform character, whether there seem to be radial variations. But first let me give credit where credit is due. So this turned out to be Andromeda is a big galaxy that extends on the sky over a large area, and therefore when you image it, even with a far infrared telescope with relatively large pixels, there's quite a lot of data to deal with. So this would not have been possible without very clever dealing with the data by Gonzalo Añano, who at that time, when we started this, he was a graduate student at Princeton. He's now a postdoc at IIS in Orsay. So this involved methods for background estimation in the images taken with various telescopes, some of them warm and therefore having large intrinsic backgrounds. The data set that we're dealing with here is Spitzer data on the one hand from archives, and then data taken from a survey of Andromeda led by Oliver Krauss at the MPI with a number of other MPI Heidelberg collaborators who got time with the Herschel Space Telescope to carry out imaging with all of the Herschel instruments. And Robert Brown and Adam Leroy helped with bring the radio data, the H1 21 centimeter observations and carbon monoxide observations into the game, because we want to compare what we see in the dust with what is seen independently through the spectral lines of hydrogen and CO. So I'm going to lead you through the highlights here. My timing on a talk like this is often not great. I'm not going to try to rush to hit every point. Let me give you the bullet results first. I hope that the timing will be such that I'll be able to talk about each one of them, but if I don't get to the ones at the end, come and talk to me afterwards. I'll be happy to tell you more. So we are able to get a map of the dust in Andromeda out to a radius of 20 kiloparsecs. Map means pixel by pixel surface densities of dust out to that galactocentric radius in Andromeda. Now, if we're willing to give up on imaging, being able to detect dust in a single pixel, but are willing to do annular averages, we can go farther out. We can get the signal to noise up by averaging over annuli and talk about the distribution of dust all the way out to 25 kiloparsecs. What do we see? We see that there's a gradient in the dust to gas ratio in Andromeda. When we bring in the gas data to compare with it, we find that the dust to gas ratio falls off systematically with radius by quite a large factor. So I would try to persuade you that we see about a factor of 9 drop from the center of Andromeda, where the dust to gas ratio is relatively high, out to 20 kiloparsecs, where it's falling off by about a factor of 9 below the central value, and well below the value that we think we have locally in the Milky Way. Now, it's very interesting that the dust to gas ratio, when you compare it with what we know about the metal content of the gas of the interstellar medium in Andromeda, something which is not perfectly known, but we study it, we don't, but other people estimate the metallicity by studying H2 regions. It appears that the dust to gas ratio actually just tracks the metallicity pretty well out to 20 kiloparsecs, an interesting result. When the metallicity, at the point in Andromeda where the metallicity is about the same as the local interstellar medium, which happens to be, as far as we know, about the same as the metallicity of the Sun, the dust to gas ratio in Andromeda seems to be the value that we have in the local interstellar medium. So some similarity in the properties of Andromeda and the Milky Way. Now, all the bullets I've talked about up till now are just using a model to interpret, and I'll explain how, but we're using a model to interpret the observations. But another question we have is, how much confidence do we have in the model? Now, in some cases, we don't have independent abilities to test the model, but actually Andromeda gives us an opportunity to test the model because there is a region in Andromeda where we actually know what the starlight intensities should be from other grounds, and we can ask ourselves whether the dust grains in that region, are they as hot as we would predict them to be, hotter, cooler? We have ability to compare, and the answer is they're not exactly what we would predict, but they're pretty close. So it builds confidence in the model. The dust model actually can reproduce the spectral energy distribution that we observe in the far infrared and submillimeter pretty well, although we do see some systematic variations in one section, in one radial range in Andromeda, where it appears that the dust properties are a little bit different from the dust properties elsewhere. Now, one element of the dust model is actually something that many people would just call a molecular feature, and that is the population of extremely small particles, which we call the polycyclic aromatic hydrocarbon particles, or PAHs, which I would regard as very small dust grains. Someone else might say they're not dust grains, they're really just large molecules. Whatever they are, they're part of the population of things that are bigger than small molecules. And they're an important part of the infrared emission spectrum of any galaxy which has them, or any region which has them. And we can use the observations of Andromeda to try to estimate the abundance of PAHs as a function of radial position in Andromeda. And you have to make allowance for the variation in the starlight that's illuminating the pause in different parts of Andromeda, because we know that the starlight spectrum varies. But after making that allowance, we find that the PA abundance in this particular parameter measuring the fraction of pause as a fraction of the dust population, surprisingly, certainly surprising to me, turns out to be relatively uniform in Andromeda. So a result which a priori was not what I was expecting to see. Okay, so those are the highlights. Let's come back to Andromeda. Here's a beautiful image of Andromeda. What I discovered is when I was looking for a nice optical image of Andromeda, the place you find the ones which are most aesthetically pleasing are from the amateur community. So they spend a lot of amateur photographers, amateur astronomers these days have access to wonderful equipment, wonderful cameras, and they put a lot of time, energy, and love into what they're doing. And they stitch together mosaics of large areas like Andromeda extremely well. So I wasn't able to find a picture from a professional observatory which pleased me as much as this one. So this is taken by somebody named Robert Gendler and made available on the web in 2005, a lovely image of Andromeda. And of course you're all familiar with this galaxy, a very bright center here, and populations of bluish light out here where coming from star forming regions, and then very conspicuous dust lanes. So you can see there's dust in Andromeda just from this image once you understand that dark spots on it, or dim areas in an image like this, are not because stars were absent there, but rather because stars are being blocked by the dust. So same phenomenon we see in the Milky Way. But it's very hard to quantify the amount of dust from an image like this. You could perhaps try to make a complicated, detailed model of the galaxy and do radiative transfer and try to put in the right amount of dust to dim the stars. But that's now a complicated three-dimensional problem where you have to specify the three-dimensional geometry. So it's a difficult way to approach the dust mapping in Andromeda. Okay, so just what do we know here? I've tilted it on the image on its side so that now north is up, and from now on I'll show the images with north up, two companion galaxies of Andromeda here, but the dust that we're going to be seeing is all concentrated in Andromeda. Okay, so what's Andromeda? Well, we're interested in it because it's the nearest spiral galaxy, about 700 kiloparsecs away. As we know by now, it's mainly dark matter providing the gravitational potential. But in that potential, there's about 10 to the 11 solar masses of stars and about 10 to the 10 solar masses of interstellar medium spread through there. So interstellar medium is not the dominant constituent of Andromeda by mass at all, but it's a beautiful and important one. So the interstellar medium, most of you are familiar with it. It's by mass. It's primarily hydrogen and helium. Significant amount of helium by mass, but the helium is actually hard to observe. So most of the time I'll just be referring to hydrogen masses. But mixed in with the interstellar medium is dust with maybe something like 0.7% by mass. That's the value in the solar neighborhood. Where now I'm referring only to the mass of the hydrogen. So from now on I won't talk about the helium. You can always multiply gas masses by 1.4 if you want to allow for the helium. It's close to us, and so we can map the galaxy with very nice angular resolution and therefore study the variation in the dust properties with position in the galaxy. And so Andromeda is special in that regard. Most other galaxies that are farther away, by the time you image them with an observatory like Herschel or Spitzer at the longest wavelengths, the angular resolution is such that the individual pixels in your image are summing over very large areas in the galaxy. Now we're still summing over significant areas of the galaxy, but now there'll be areas that'll be of order hundreds of parsecs instead of kiloparsecs added together. So why do we care about the dust? Well, because it's a very important player in the physics of the interstellar medium. So I'm not going to tell you any details here, but if you want to understand what goes on in the interstellar medium, you've got to understand what the dust is doing, not just that it's there, but the way in which it acts upon the interstellar medium, either shielding gas by its role in radiative transfer, dynamics of the gas, radiation pressure pushing on grains and the grains pushing on the gas, the chemistry of the gas, because molecular hydrogen is predominantly formed on the surfaces of dust grains, and many other molecules are then built out of the using the molecular hydrogen bonds that were formed on the dust grain surface, and the heating, cooling, and even the ionization balance of some parts of the ISM are strongly affected by the presence of dust grains. Okay, so that's the motivation. Now, how do we go about this? Well, we've taken the data available for Andromeda at all infrared wavelengths Spitzer or from the Herschel Space Observatory. So there's 2 cameras on Spitzer, the IRAC camera, which Giovanni Fazio has made available to the world through his work on leading the IRAC effort. The MIPS camera at longer wavelength, and then Herschel has 2 cameras, the PAX and Spire cameras, operating with broadbands centered at these wavelengths. Now there's some redundancy here between the bands of Spitzer and Herschel, so you may wonder, why am I using Spitzer data at 70 and 160 microns when I have more modern data at exactly those at bands centered on the same wavelengths? Well, the answer is that the 2 data sets are actually not perfectly compatible. So the photometry with the 2 different cameras of the same regions of a galaxy, particularly when it's faint, they don't give the same value after all the processing that's done by the 2 camera teams. Which one is right, I don't know. Each one says the MIPS team says their data are the ones to use, the Spire team or the PAX team says the contrary. We decided it's better to use both data sets, and we'll be somewhere in between. We'll neither be perfectly right, but we won't be spectacularly wrong either. So that's the compromise we took to avoid, giving serious offense to either of the teams. Also, I think it's the right thing to do. We're just adding more data in. It was careful, well-taken data, and there's no reason to think it's of any lower. Either of these data sets are less reliable than the other. And then from the ground, there's interferometric imaging with Westerbork at 21 centimeters, and then the 25-meter IRAM telescope has mapped the galaxy, not all of the galaxy, but quite large areas of the galaxy, wherever the molecular hydrogen is abundant, where the CO signal is strong, out to 11 kiloparsecs. Okay, now as I said already, an important part of the infrared story here is to do background subtraction. You have to figure out how much of the flux you're getting in a pixel is actually just background or foreground emission. Emission from the telescope, emission from dust in the Milky Way, emission from background galaxies, and the background galaxies become significant in the outer parts. We're going out to areas of Andromeda that are faint enough that the background galaxies begin to contribute a significant fraction of the flux. So I think we do a job of background subtraction, which is very good. It's a very hard problem, but I think we've done a very good job out to about 25 kiloparsecs. So I won't have a chance to persuade you of that, but if you have questions, we can talk afterwards. Except for 2 of the bands, the IRAC 6 and 8 micron bands, for some reason, it should be 5.8, it's 6 microns and 8 microns, a typo there. For some reason, there seem to be some artifacts present there when you get down to the lower intensity levels, and so we're not able to go quite out to the radii that we could at the other wavelengths. Okay, so now I've the same optical image I showed you before at the same scale, and now here's a map of the same area of the sky at 350 microns from the Spire 350 micron camera. So same spatial scale, same angular scale here. You can see how far out we're getting significant detections of the far infrared emission or submillimeter emission from the dust grains. The smooth, the annulus here is a 20 kiloparsec ring at the inclination that we think M31 has based on observations at 21 centimeters. So we're basically detecting the dust through most of the galaxy all the way out to 20 kiloparsecs in single pixels, right? So this is a map with each pixel independent of the pixels, except maybe the adjacent pixels are a little bit, there's some overlap of the information from one pixel to the next door neighbor pixel, but basically independent pixels here. And if we'll need to average over larger areas, you can get out beyond this 20 kiloparsec ring. They're just not there. So the satellite up here it would be there, but it's not very bright. The elliptical satellite down here just doesn't have any dust in it, so it doesn't show up at this band. If you had 3.6 microns, you'd see it. Okay, so how do we go about the modeling of this? So the data we have, I showed you 350 micron data. I'm not going to show you all the other bands, but the galaxy has morphologically a similar appearance in the other bands as well. 350 microns is a particularly nice set of data, so it was a nice one to show to you. We take the multi-wavelength data and the first thing we do after background subtraction is we convolve all the images to a common resolution. We have to choose what resolution we want, but we want all of the modeling to be done on a map that's done at multi-wavelength map at a common resolution. So that's an essential thing. If you want to get the colors right, you've got to do that first. So we choose two different resolutions here. We do some of our modeling at the Spire 350 resolution, which has a full width half maximum of about 25 arc seconds for the beam. We sample it with pixels that are about half that size. But we also try larger pixels, which allow us to, a larger PSF, 39 arc second full width half maximum PSF of the MIPS 160 micron camera, in order to be able to use the MIPS 160 micron data. Because if we restrict our study to this, we can't use the MIPS 160 data and we can't use the Spire 500 data. So we have a choice here between two modelings, one with relatively good angular resolution but not using the complete data set, and another one where we degrade our angular resolution but bring every camera into play. So more information, higher signal to noise. And one question one reason we do this twice is we want to see, do our answers depend on which way we do this? If we get very different answers both ways, then you're going to be suspicious of both answers. But if we get similar answers with the two techniques, you're going to be convinced, okay, the resolution is not the issue here, and in fact the redundant information, the extra information brought in by Spire 500 is not a critical part of the story, that we can get the same answer even if we didn't use that information. In other words, the model must be pretty good if it's able to get along with, even after taking away some of the data at the longest wavelengths. Okay, so what's the model now? So again, I can't go into this in detail, but we have a model that we've developed for interstellar dust, which has been developed over many years, attempting to find a physical model which we can specify the model and do calculations for, because we have an idea of what we're doing the calculation for, and which is consistent with observational constraints that we have available to us. Now, what observations do we primarily use? We started off using the observations of extinction to stars near us in the galaxy. That's the best studied. The best cases for studies of extinction by dust, the wavelength-dependent extinction, is to use stars that are within a kiloparsec or so of us, and there are many such stars that have been measured. We have a pretty good knowledge of the wavelength dependence of interstellar extinction from the near-infrared, say 2 microns, down to the vacuum ultraviolet wavelengths of maybe 1100 angstroms. So that's data that's been developed through many efforts, including space-based and ground-based observations over the years, and it should inform our dust model and constrain our dust model. We don't want a dust model which can't be made consistent with those data. So the size distribution of the particles that we use is one which was adjusted to be compatible with these observations. In addition, we have observations of the infrared emission from certain regions that were observed, which require a population of polycyclic aromatic hydrocarbons to explain it, through single photon heating of the very small particles. They get heated up to temperatures that can be 500 or more degrees at peak, and they can radiate at wavelengths as short as 3.3 microns, 6 microns, etc., to reproduce the pH emission spectrum. So that's the PAS are part of the model. The size distribution that we use for the PAS, I'm not going to have time to talk more about this, but it's one which is actually consistent with the observed spectrum of anomalous microwave emission. In other words, the PAS that we put into our model here, if you calculate the microwave emission that we produce by their rotation, it's essentially compatible with what we know about observations of the anomalous microwave emission. Now, the dust is going to then be heated by starlight. So we're going to assume that the dust in Andromeda is the same stuff we have locally in our Milky Way. The models have been developed locally, except we will allow ourselves the freedom to adjust the PAH abundance up and down, because that's something which we have evidence that it does vary from galaxy to galaxy. And so that's a knob that we're going to have in our model. I'll talk about how many adjustable parameters we have. The dust is going to be out there in Andromeda, and it's going to be heated. What's it going to be heated by? It's going to be heated by starlight. That's what the predominant heating mechanism for dust in our galaxy is: absorption of starlight photons. Heating of the gas, or heating or cooling of dust grains by collisions with gas atoms, is unimportant except in unusual regions. So in the diffuse interstellar medium, that's a tiny correction to the heating, cooling of a dust grain, so we don't worry about it. So we need to specify the starlight in different parts of Andromeda that's heating the dust. Once we specify the starlight, then for each grain in our dust model, we need to solve for the temperature. Now the temperature is not one number, it's a temperature distribution, a probability distribution function, because the process of heating the grain is a stochastic process. Photons are arriving randomly. If you have a very large grain, the photons will arrive frequently, be absorbed frequently, and the heating can be treated as a steady heating rate. But for very small grains, the heating is very stochastic. So here's an example in a radiation field that's 100 times stronger than the one where we are in the Milky Way. So I've raised the radiation field just to get the photon absorption rate up to large values. A grain with, say, 4,000 carbon atoms would have a temperature history over 1 day. This is about 1 day here, 10 to the 5th seconds, which would look something like this. It'd be jumping around between, sometimes going below 10 degrees Kelvin, sometimes jumping up to 70 or 80 degrees Kelvin, depending upon the luck of the arrival of photons. And a grain with 500 carbon atoms, the photon arrivals are essentially, by the time the next photon arrives, it's radiated away all the energy from the previous photon. So it's now in the single photon heating limit, where you can just, the spectrum doesn't depend upon the intensity of the photons, the arrival rate of the photons, because each photon is an independent event. Okay, so we calculate the temperature distribution function, we solve that problem, and then we can calculate the resulting infrared emission spectrum. Okay, so I've already shown you that. So just to see, this would be for a starlight intensity like the value in the solar neighborhood. Our small grain here would have a good chance of going an entire day without absorbing a single photon. Life is dull for that grain. Okay, so now we calculate these temperature distribution functions for each grain. Of course, we do sample our size distribution to a finite number of sizes, and we have each composition that we include in our model. It's amorphous silicate, and graphite and PAS are what are used in the dust model. And then for each starlight intensity, we would then predict an infrared emission spectrum. So here's what the spectra would look like from 5 to 1,000 microns, or 2 to 1,000 microns. These are spectra for different starlight intensities, where the spectra, the emissivities have been divided by the overall starlight intensity. Obviously, make the starlight intensities higher, the emissivity per grain or per hydrogen atom is going to go up, but we can normalize that out and then keep all these different plots more or less at the same peak value, and just observe the shifting of the peak from long wavelengths when the low starlight intensities and the grains are cool, to short wavelengths when the starlight intensities are high and the grains are typically heated to higher temperatures. Notice that the very short wavelength part of the spectrum stays invariant here. That's because that's dominated by the single photon heating process. So again, the photons just arrive more frequently, but each one produces the same resulting emission spectrum as the grain absorbs the photon energy and then radiates it away as it cools down to very low temperature before the next photon arrives. So that's a nice feature of the model, is that it has this insensitivity of the short wavelength emission to the intensity of the dust grains, and that's in fact what we observe in galaxies. Galaxies would seem to have very little variation in the pH emission spectra, or the emission spectra of the short wavelengths. Okay, so the modeling here proceeds by, as I said, we convolve to a common resolution. Now, for each pixel at this common resolution, we then are going to try to reproduce the spectrum of emission from that pixel. What do we have available to adjust? Well, we don't know how much dust is in that pixel a priori, so that's clearly one free parameter. So we will have a total dust surface density. I should say each pixel at the shortest wavelengths we see starlight. So 3.6 microns, the IRAC camera is basically seeing the stars. There's very little emission from the dust there. So we want to subtract the starlight at longer wavelengths, and so we use the shortest wavelengths to tell us how much starlight is there, to extrapolate the starlight to longer wavelengths. So for each pixel we do also have a starlight intensity, a starlight surface brightness. We assume just a moderate, typical stellar temperature, because we're doing this in the Rayleigh-Jeans limit of the spectrum, so it doesn't really matter what temperature the stars are, just how bright they are at 3.6 microns. We adjust the total surface density of dust. Now we have a starlight properties are also to be adjusted. We don't know how intense the starlight is in our pixel, so there's a parameter which I'll call U min here, which would be the typical starlight intensity seen by most of the dust in that pixel. But these pixels are now going to be hundreds of parsecs on a side. And so by the time you sample a region of Andromeda that has 10,000 square parsecs of surface area, there will be different regions within that. There may be small star forming regions in there, big star forming regions. And so we know there won't be one starlight intensity heating all of the dust in that region. So we actually allow ourselves two more parameters here to allow for a distribution of starlight intensities to higher intensities. So the idea here is that a small fraction of the dust in the pixel may be relatively close to a star forming region, relatively close to a star, and therefore would see higher than the average starlight intensity. And so we have two parameters. I won't explain what I mean by what their significance is, but they control the intensity of the higher intensity starlight heating. So now we've got 1, 2, 3, 4, 5 parameters, and then finally we can adjust the pH abundance. So we have 6 parameters for each pixel, but we have observations in 11 bands. So we are at least over-constrained here, bands from 3.6 to 500 microns for the case where we use all of the data. Okay, so here are just 2 images to show you the effect of degrading the resolution. So here's an image, that same 350 micron image I showed you before, and now the 350 micron image degraded to the resolution of the MIPS 160 PSF. So it's blurred a little bit, but the important thing is that you can see most of the structural features here. You can track them here. Obviously, this is not as sharp as that, but you would get most of the structure of Andromeda from this image that you see here. Okay, now what's the PSF size here? Well, the PSF is 140 parsecs would be the full width half maximum of the PSF, and here it'd be 90. So that's telling you how much of the area of the galaxy we'd be averaging over. Of course, that's projected on the sky. The galaxy is tilted, and so along the minor axis direction, where the linear extent on the surface of the galaxy would be higher. Gary?
Quick question. In some of those bands, they're very strong gas phase emission lines. At 160, you're very close to the C+ line at 158 microns. Has that been accounted for?
We've not corrected for that, but it's not a significant correction. The band is broad enough, and most of the dust is so luminous compared to the C2 line that the C2 line has a very small amount of flux in the 160 micron band. But you're right, it's in that band, and it's part of what we see. But it's a small correction compared to just the overall calibration uncertainty. So we didn't bother trying to do that. In cases where the C2 spectroscopy has been done, not in Andromeda, I mean, maybe somebody's done it from Andromeda, certainly for other galaxies, you can tell that the flux that's seen in the C2 line would be a small correction to the PAX 160 micron band or the Spitzer 160 micron band. Okay, so and again, the advantage here, there's some artifacts in the production of this image here, which are not part of the data set. It's just somehow producing a slide, you get these bands on here, turning it into a EPS file, etc. But the signal to noise is improved in going from this image to this image, and will allow us to go further out. Notice this curious gap here. So when I first saw that gap, I thought, oh goodness, we got a real problem here with our background subtraction. We're obviously over subtracting the background at this end of the galaxy. Turns out that's not true. You'll see that there actually is a dramatic deficiency of dust in that corner of Andromeda. Okay, so this is the infrared luminosity, the surface brightness of the far infrared emission in Andromeda. So it runs from very high values of up about 10 to the 8 solar luminosities per square kiloparsec. And we're able to measure it down to values which, well, let's say this green shade here would be about 10 to the 6 or a few times 10 to the 5 solar luminosities per square kiloparsec. And then, in view of the time, I'm going to jump forward. This is just showing the annular averages of the surface brightness, showing you that in the outer parts of the galaxy it seems to obey more or less an exponential fall off, but it's certainly not an exponential surface brightness from the center out here. The exponential fall off only begins at 11 kiloparsecs. So the idea of exponential disks is a nice one, but it's certainly not an accurate description of what we're seeing in Andromeda. Here is a fraction, so we have adopted a policy here that when the surface brightness of a pixel is less than a certain minimum value, surface brightness integrated over all the bands, when it's less than about 1.5 times 10 to the 6 solar luminosities per square kiloparsecs, then we figure our signal to noise is getting now low enough that it would be dicey trying to estimate how much dust is in that pixel. So we don't try to do that below a certain threshold. that threshold is where this irregular contour goes. So again, this corner of the galaxy falls below that threshold. And here is the fraction of the pixels at each radius that are above our threshold. So it's basically 100% out to 15.5 kiloparsecs, and then begins falling off as we go out. Okay, so now here let's get to the model results. So the dust surface density. So again, for each pixel, we've estimated how much dust surface density we think is present there. And here's a map of the dust surface densities in solar masses per square kiloparsec of dust, which are actually low at the center. So the galaxy is bright at the center, but that's because the dust is hot there. There's relatively little dust right in the center, a lot of dust out in this radial ring here. This ring reaches surface densities which, if you multiply by cosine of the inclination to get what you would see if you were looking face down on Andromeda, get up to about 10 to the 5 solar masses of dust per square kiloparsec. And that peak is about 11 kiloparsecs out. Now, this is there's 3 sets of symbols plotted on here. The 2 triangles are cases where we do annular averages, but we only include the pixels where the surface brightness of the dust is high enough that we trust the modeling on a single pixel basis. The circles here are where we draw annuli here, tilted annuli, and then sum up the flux in the entire annulus, including the low surface brightness regions, and then take that summed up flux and say, okay, if that's the total flux I have, what dust mass, what starlight intensity do I need to reproduce it? And then use that dust mass to get an average dust surface density for that pixel. The circles are the more complete way to go because they allow us to include the fainter pixels. When we go to single pixel modeling, we're throwing out all the faint pixels, which is obviously going to bias us because those faint pixels do have some dust in them. So when we do the circles, first of all, it agrees up to about 17 or 18 kiloparsecs. The results are the same. But out here, we see more dust when we sum up the fluxes over this annulus, and it seems again to have an exponential fall off out to 25 kiloparsecs. The total mass of dust that we see is about 50 million solar masses of dust, according to our dust model. So again, the dust model is one which is imperfectly calibrated. So there may be overall, the model itself may be wrong, and so maybe our dust mass estimate has some overall multiplicative uncertainty, but probably, I would say, probably not more than a factor of 2 uncertainty, and so it turns out to be a reasonable value for the dust mass, as we will see when we look at the dust to gas ratio. Okay, so the dust to gas ratio. Here's what we looked at before. This is the model of the dust surface density, a model that reproduces the far infrared emission SED for each pixel. Here is the observed gas surface density. Same angular scale, same boundaries drawn here so you can do comparisons. Notice that this area where we were missing dust, where I had this reaction of horror when I saw that. I thought, goodness, we're missing something there. We've over-subtracted the background. It's deficient in H1. Something dramatic happened in Andromeda to reduce the surface density of H1 in this corner of the galaxy. So I don't know what happened. I've talked to the people who do dynamical modeling of the local group, and there are various hypotheses for interaction with companion galaxies, other members of the local group. There doesn't seem to be any explanation that really seems like an attractive interpretation of why this has happened. But clearly, gas is missing here and dust is missing there. And it must have happened within the last several hundred million years, otherwise it would have phase mixed out, and it would have been smoothed out by differential rotation. Okay, now if we can take our dust map, divide it by the gas map, remember this is an independent data set. No information from here was used in producing this. We divide this by this, we're going to get a dust to gas ratio in each pixel. Here's what that looks like. Same angular scale, same ellipse drawn here. I've only shown you the dust to gas ratio for the pixels where I think I can estimate the dust mass, where the signal to noise is high enough. So I don't want to show you crazy results in the outer parts where the low signal to noise leads to absurd values for the dust surface density. But notice that much of the structural information of the galaxy has actually disappeared once we divided out these two maps. In other words, where there's more dust, there's more gas. Where there's more gas, there's more dust. So we do see a strong radial trend, but very little we see some non-radial structure here, but the main structure we see is a radial variation going from high dust to gas ratios to low as we go from center to edge. Now the scaling here, the color bar here is the dust to hydrogen mass ratio multiplied by 100. So a 1% value would be this color of green here. And so you see a 1% value is occurring, somewhere about, 10 kiloparsecs radius. Here are the single pixel values here. So we just plotted every pixel where we had a detection just to give you some sense of what the scatter is at a given radius. Okay, so let's see, did I forget to say? Yeah, so the dust, so we see a gradient here from values that are, of order 3 or so at the center, 3 or more, down to the outer points here where we're beginning to lose a signal noise, but we're getting down to this blue region where it's maybe 0.3. So we see a dynamic range of about a factor of 10 in the dust to gas ratio in this image. Okay, so here's again, here's now a plot of the dust to gas ratio versus radius, and again, 3 sets of symbols here, or 2 sets of symbols. The triangles were single pixel modeling at MIPS 160 resolution, and the circles where we've integrated all the flux and all the gas in annuli, and then done modeling to estimate the mass of the dust in the annuli. So the dust to gas ratio seems to fall from about, and I've normalized it here as again 100 times sigma dust times sigma divided by sigma hydrogen, so a value of 1% would be 1 here. We think the value in the solar neighborhood is about 0.9% based on detailed studies of the gas and the elements that are missing from the gas. So the solar neighborhood value would be about here. That happens to occur at about 10 or 11 kiloparsecs out. And the 2 data sets agree pretty well out to here. There's some discrepancy at 20 kiloparsecs, but I'd say the circles here are the ones to go with. Here are 2 other estimates from a separate study of Andromeda by another group, which call themselves Helga. So Helga 1 and Helga 2 are 2 papers produced by that group giving their estimates. So we get similar values as they found with their approach to the modeling. Okay, so now let's compare this to the metallicity. What do we know about the metallicity? Well, the metallicity of the gas is obtained by people who study the spectra of H2 regions. They observe the line emission from metal ions in the H2 region that are collisionally excited. If they think they know the temperature of the gas, and of course they have also hydrogen lines from the same H2 regions. So if they think they know the temperature of the gas, they can estimate how much of oxygen, say, has to be in the gas phase to produce the lines of oxygen 2 and oxygen 3 that are observed in the emission spectrum. So the oxygen abundance is calculated this way using a temperature. Now, if you have really good data on the oxygen lines, you can actually determine the temperature of the gas from line ratios. But the line ratios include a line that's relatively faint. So you need a relatively good measurements. Over part of the galaxy here, it was possible to get the gas temperatures. This is a study by Zarita and Bresolin. So they were able to get gas temperatures using these weak lines. And so they're not guessing the gas temperature, they're getting the gas temperature from the observed spectrum and then calculating the metallicity from the strength of the oxygen lines relative to the hydrogen lines, and that's their value here. In the dashed regions here, they had to use other methods to estimate the gas temperature because the weak oxygen line was too weak for them to detect. Either too weak because there's too little oxygen or in the outer parts, or too weak because the gas is too cool. The H2 region has so much oxygen in it that it's cool, and the weak line comes from a higher level that requires, that's hard to excite. So they extrapolated here. Now notice that our results in the region where theirs are most reliable, we actually have a ridiculously good agreement. So, when I put these things on top of each other, I was shocked by how close how the trends seem to match. It wasn't designed, we had no knowledge of the H2 region data prior to, we didn't use that data in our estimates of the dust to gas ratio. In the inner parts, we get significantly different results, and the outer parts, we get significantly different results. And your guess is as good as mine as to, which approach is more reliable. I don't believe we don't have a precision method here, but on the other hand, maybe they were getting using wrong estimates for the temperature out here and here. So the main result here is that over much of the galaxy, we're tracking the H2 region abundances are very close in their radial dependence to the dust to gas ratio, which we measure. And where the dust to gas rate, from where the metallicity is the same as in solar neighborhood value, the dust to gas ratio ends up being the same as what we think the dust to gas ratio is in the solar neighborhood. So the interstellar medium of Andromeda is like the interstellar medium where we are. Now we also estimate the starlight intensities because the dust in each pixel is hotter if there's more starlight there. Here's a map of the average starlight intensity in each pixel. As I said, each pixel actually has a distribution of starlight intensities. This is the average, the dust-weighted average within that pixel of the starlight intensity. It's very high at the center. So there's a very bright starlight if you're at the center of M31, and it falls off to low values out here. Again, we think the solar neighborhood, the diffuse interstellar medium, the solar neighborhood value is what corresponds to 1 on this scale. So green would be starlight intensities like we think we have around us, and it's reassuring that, looks like the starlight in Andromeda at 8 or 10 kiloparsecs from the center is like the starlight here. So here's the starlight intensity, but now taken to the 1/6 power and multiplied by 18 degrees Kelvin as an estimate for what a typical dust temperature would be. So the typical dust temperatures at the center are getting to be 30, 35 degrees, but falling off, sort of about 10 kiloparsecs or 17 degree-ish, and falling off very gently in the outer parts. It's only going as the 1/6 power of the starlight intensity. So the dust temperatures don't vary very dramatically. Now, the starlight intensity at the center is something that we actually can calculate because there are independent studies, detailed studies of the stellar bulge of Andromeda. People know how many stars are there. They know what kind of stars they are, what the spectra of those stars are, and what the three-dimensional distribution of those stars is. And there's very little dust there to block the starlight. So the low abundance of dust in the center of Andromeda is actually fortuitous for us because it allows us to have an a priori or an independent estimate of the starlight heating rate, which we can now compare with the estimate of the starlight heating rate that we got when we used the dust grains as photometers. Up till now, we were basically using the dust grains as photometers. We don't have an instruction manual for them, so we're guessing, how the dust grains glow, what spectrum they glow with when they're heated by a certain intensity of starlight. Now we have an independent determination of the starlight intensity that we can use to compare with our estimate. So let me just zoom in on the center here. So this solid line is what we would estimate the the dashed line here is a starlight intensity that we would calculate for the bulge stars. I should say starlight heating rate. And this is sort of a guess for what the contribution of the disk population might be. It not very meaningful, but it's also not important at the center. It only becomes important out at 2 or 3 kiloparsecs. And this solid line is the sum of this simple exponential disk and the bulge which we calculate. And the triangles here are what we measure from the dust grains. So it's actually, to me, very good agreement between the starlight intensity that we think is there and what we measure from the dust grains. Now we get slightly lower values with our dust grains, so we seem to be missing something a little bit in this comparison, but overall this to me is reassuringly good agreement. So what that's telling us is that the dust at the center of Andromeda is really not that different from the dust in the solar neighborhood because that's what we use to calibrate all of this. Okay, now I said we could talk about the pH abundance. So now each pixel in the galaxy, we have emission, and with the IRAC camera has 2 bands at 6 and 8 microns, which are particularly sensitive to pH emission features. And we empirically know how to determine the strength of the pH emission into those bands, and therefore can estimate from the strength of the emission in the 6 and 8 micron bands what abundance of pHs we need at each point in the galaxy. And this is now the pH abundance, which is expressed as this parameter QPA, which is the fraction of the dust mass contributed by pHs that have less than 1,000 carbon atoms in them. So it's just to be specific about what we're talking about. And we think in the Milky Way that value is something like 5%. So 5% would be green here, so the Milky Way value would be green. Now, there are strange radial trends here where there's, their outer parts here seem to be I think the structure we're seeing here is not entirely real. We've done our best job of background subtraction, but there seem to be some artifacts in these images in the faint outer parts, which we're having trouble with. It could be due to structure in the pH emission in the Milky Way, which is a significant foreground that we have to subtract. But in any case, the net result, after we average over annuli again, is that, okay, there is variation in the pH abundance, but I wouldn't press my case here for arguing for real variation. My main conclusion is that it's more or less constant from center to the outer parts at maybe 4.5%. You could debate whether the variation is real or not real, but the main point is that it's relatively uniform, given that the dust to gas ratio itself is changing by a factor of 10, the fraction of the dust which is contributed by pHs seems remarkably constant. Okay, so how well is the spectral energy distribution reproduced? Well, I've just picked two bands here, Spire 250 microns and Spire 500 microns, a relatively short, relatively long wavelength band, and asked the question, okay, we fit our model to the measurements in all the bands. Now if we just go to one band and compare the model to the observation in that band, how well do we do? So this is the ratio of the model emission to the observed emission in each pixel at Spire 250 and at Spire 500. So green, 1 would be ideal, so green is good, and most of the galaxy is greenish. There do seem to be significant trends here with the central area being below 1, the outer area tending to be above 1 at 250 microns, and again, some radial tendencies are visible here, but again, green is good and most of the galaxy is greenish. So it's a rough, we're doing reasonably well here. We don't see any dramatic failures of the model with radius. If I allow myself now to tune the model if I say, okay, I'm going to go change the spectral index of the dust opacity at long wavelengths, can I improve the agreement by doing some adjustments? The answer is yes, you can improve the agreement if you make the dust spectral index a little bit steeper in the 1 to 6 kiloparsec region here, or 2 to 6 kiloparsec region. So modest steepening of the dust opacity, whereas overall most of the rest of the galaxy, this dashed line is what we're using, and so the best value is not very different from what we actually have already in the fixed model with no adjustment. So there may be some variation in the dust properties in the 2 to 6 kiloparsec region. They're not dramatic, but they do seem to be real. So the dust is not the same everywhere. Okay, so I guess I managed to get to the main results. I showed you all these bullets before. I hope I've persuaded you a little bit. I'm going to take the opportunity now to talk about one more thing here. So Andromeda is very interesting, but one thing we'd like to know in addition to how much dust, and the dust is not the only interesting thing about Andromeda. People use Andromeda as a place to calibrate the brightness of stars, to test, our models of our understanding of stars, and that, of course, requires knowing the distance to Andromeda. Now, currently, the distance is only known to 4.5%, and that's the best determination using eclipsing binaries. So it's a hard problem, and this seems to be the value to date. There may be other ways to approach it, but one way in which you could measure the distance to Andromeda, in principle at least, is to use the fact that nature has kindly placed a QSO, an AGN, a radio galaxy, an X-ray source behind Andromeda at this position, where there's a significant amount of foreground dust, a dust in Andromeda. So this has been previously detected by Einstein and Rosat. We know it's a BLAC object. It doesn't have a redshift. But it shows variations in its X-ray brightness with time. So the fact that it has a fluctuating X-ray brightness gives us the opportunity to look at the X-rays that come from the AGN far away and are scattered off the dust in Andromeda and then received by us. So if we image Andromeda in X-rays, we will see a component of scattered X-rays coming from the AGN far, far away, scattered off the dust here. Of course, when the AGN fluctuates, that leads to increased surface brightness of the photons reaching Andromeda, but the photons that are scattered by the dust here will arrive to us later than the photons that would come undeflected at the center here. So by looking at the time-delayed surface brightness of Andromeda and X-rays, you could get a geometric determination of the distance. So it may be feasible to do with Chandra. It would require large amounts of observing time to get a statistically significant result, but Nick Bond, who was a graduate student at Princeton when we worked on this, and we did simulations of what the light curve, what the X-ray scattered light curve of Andromeda would look like, and decided that if the fluctuations in the AGN were more or less what we expect them to be, there'd be a good chance in an observing campaign of having the AGN fluctuating by enough that you get a statistically significant determination of the time delay. The time delay is a function of the angular distance of the X-ray received from the center here with greater time delay, and the time delays here are like 100 days. So you could do this out to 100 arc seconds from the source, and you get time delays of 100 days. So it's a long observing campaign, but something that could in principle be done, and you might be able to improve on the distance that's gotten from the eclipsing binaries. So let me thank you very much for your attention.
Thank you very much. Bruce will take questions if there are any. Well, let me start off. Is the mass of the dust predominantly in grains of one relatively narrow size range, or are they more or less uniformly distributed over the...
Well, the size distribution, our knowledge of the size distribution of dust is primarily informed by measurements of the wavelength dependence of extinction. And that's something which is, work is continuing in that. I spent some time talking to Charlie Lott about this today, and the results which are gotten as we extend the wavelength range over which we're able to do this into the infrared, the results we're getting are challenging our interpretation. But the results that were based on observations from, say, 2 microns to 1100 angstroms can only be reproduced by models that have most of the dust mass in grains that are, say, between 0.1 and 0.3 micron in radius, if you want to imagine them to be spheres. They're not spheres, of course, but if they were, that'd be their range of sizes. Most of the dust surface area is in smaller grains. So it's a size distribution which, if you wanted to approximate it by power law, it's not a power law, but if you want to approximate it by it, there's the famous power law is Mathis, Rumpel, and Nordzig. DNDA, number of dust grains per size interval, goes as 10 to the minus 3.5. So you can immediately work out that has most of the mass at the high end, most of the area at the small end, and that's a rough description of what we have. We think we have more realistic size distributions than that simple power law, but that's what nature has done. There may be some very big grains out there. So if you said, well, nature sometimes makes grains that are 2 microns in size and puts 10% of the dust mass into those grains, they would be very hard to detect. So we don't claim to have a complete inventory of the big grains because you could hide some up there. And there's in fact a lot of controversy over what the large grain population in there. I could give you a colloquium about that controversy because there are measurements made with spacecraft, interplanetary spacecraft that appear to be detecting dust grains coming in from the interstellar medium into the solar system, hitting the spacecraft. They have particle detectors on the spacecraft designed to measure this, and they can infer the dust mass from the kinetic energy of the impact. And they claim that they are getting impact rates from grains that are up in the 1 micron range that are well above what I would have thought to be possible for the average interstellar medium. Now, we're only at one point in the interstellar medium. Maybe it's a weird place that has an unusual excess of large grains. It's hard to buy that argument, but it's also hard to see what's wrong with the spacecraft measurements. So this is one of the mysteries that we have yet to sort out.
Bill.
Bruce, factor of 10 variation in dust-gas ratio seems like a lot, at least to someone who used to think it was constant. Can we expect a similar result in the Milky Way?
Well, I don't know enough about the metallicity gradient in the Milky Way. Perhaps somebody here wants to comment on it. I was surprised that the metallicity gradient in Andromeda was as steep as it's reported to be, although remember, our dust-to-gas ratio does fall off more than the metallicity ratio as extrapolated from inwards and outwards by Zarita and Breslin. So the inner parts of Andromeda, I don't see how our dust-to-gas ratio, our dust model could be wrong, so there could be systematic problems in the dust model. But if the dust model were correct, then we couldn't have more dust in the center of Andromeda than is allowed by the metallicity. So I would say if we see a high dust-to-gas ratio in the center of Andromeda, then maybe we're missing some of the gas, except we've asked ourselves, could it be in an ionized form that we're not counting? Could it be in a molecular form and somehow missed? And the answer seems to be no. Or the metallicity determinations are wrong, and there's actually a higher metallicity at the center. The outer parts of Andromeda, so it's easy to imagine you could have dust-to-gas ratios that are low because you just don't make dust grains or they don't survive. So it's quite possible that in the outer parts of Andromeda are more rapid fall-off in the dust-to-gas ratios because less of the heavy elements in the outer parts are in dust. So I should have mentioned that in the regions like around us, in the galaxy, we measure the abundances in the gas phase of things like silicon and magnesium and iron and titanium, and they're mostly missing from the gas. Those elements are 90% in the dust grains, i.e. mostly in the dust grains. But it didn't have to be that way. If you had a galaxy with lower metallicity, you could imagine greater difficulty in maintaining a high fraction of the metals that are there in dust grains. But that's, again, a question of dust grain evolution. So I don't know. Again, maybe this would be seen in the Milky Way. I don't know how we'd measure it. It's tough being in the middle of the disk where you can't see the outer parts very well.
Ramesh.
Yeah, so, Bruce, when I look at the optical image of M31, looks like there's definitely a war. But your infrared images didn't show it. Is it that the dust is not participating in the war, or is it there?
Well,
do you allow for it when you do your...
Well, of course, when you're looking at the outer, well, there is a warp, and there's a warp in the gas. So when I say we assume it to be coplanar, in our model we assume coplanar because for the dust modeling it's not critical. But the radio observers who study the 21 centimeter line in detail, they have a warping of M31, which is actually as a function of radius. So there isn't just, it's a complicated solution that they get. Whether you'd expect to see that in the coarse observations of the infrared emission, I wouldn't have expected to see a warping showing up very much. So I'm not sure.
Your pictures
so here's
really beautiful ellipses. Yeah.
So well, I mean, the ellipse. Of course, the white is a beautiful ellipse because it is an ellipse. I'm not sure that I see the irregularity. To me, the most dramatic thing here is, the thing that jumps out at me is this deficiency here. So if I can't understand that, then I'm not sure I would be able to interpret variations in surface brightness in terms of variations in the tilt of the galaxy.
But you would generally expect the dust to follow the gas.
The dust should follow the gas. They're not perfectly coupled, but they're coupled well enough it's hard to separate them. So you have to have sustained effects to separate them. They can be separated, so it's not a one-to-one thing for sure. But as the starting point, I'd assume fixed coupling.
Gary.
The other feature of dust is that they're host to ice mantles. Do I infer from the non-mention of ice in any of this modeling that it's sort of irrelevant to this analysis?
Well, the ice mantles are known to only be present in regions where visual extinction is more than 3? I think it's about 3. And if you ask what fraction of the interstellar medium is shielded that way, it's a small fraction. Right? Diffuse molecular clouds are less than that. They have molecules, but they don't have ices in them. So you're really not missing. Let me put it this way: when we're modeling the gross infrared emission in these big pixels, we're not sensitive to any part of the interstellar medium that is subdominant in the mass if the dust grains there are cold, because cold dust grains don't radiate very much per unit mass. And if you put a subdominant fraction of the mass in there, you just will never notice it. You can only notice dust grains with a small mass if they happen to be remarkably hot or something. So our models are just not sensitive to the small amount of interstellar medium that is actually heavily shielded. Notice we don't allow starlight intensities far below 1. Well, actually, we do allow it, but we don't fit them in the central part of the galaxy. Even though I'm sure there are dark clouds there, they just make a minimal contribution to the overall spectral energy distribution. You need to be able to zoom in on a dark cloud to study that, that aspect of the dust. So you need to do studies in our galaxy with something like Herschel, zooming in on a dark cloud to see the characteristics of the dust there.
Go ahead.
Have you compared your results to the dust map from FAT? Have you compared your results to the dust map from FAT?
Well, I haven't seen a dust map from FAT except unofficially. I don't know if one has been published. And that's going to, I should have mentioned that. This is an important point. So we've made our prediction here for the dust mass. And the FAT survey, Penn, Hubble, I don't know, anyway, Andromeda Treasury is the AT, led by with Julianne Dalcanton and others, is a wonderful study that's going to, that is or has already imaged Andromeda with large areas of Andromeda with Space Telescope, detecting millions of red giants. And each red giant they can do photometry on. And they can determine, and red clump giants you think you know the intrinsic color of very well. And so you can determine the reddening to millions of stars in Andromeda. And so their reddening maps are going to be immediately, will be compared to our predicted dust surface density maps. And it may well be there'll be a systematic offset. We've predicted the dust surface density based on our modeling of the dust, and it's only a model. And so they will be able to test that model, and with whatever results come out of their survey, the next generation of models may have to make significant adjustments to. So the hints that I've seen, well, from what I've seen unofficially, they are detecting lower extinction than we would predict. And so maybe we've overestimated the dust surface densities here by a factor which could be as large as 2.
Randall.
Obviously, in Weingartner and Draine, you had tweaks to the model, to the different dust models as the metallicities changed. Did you consider any of those tweaks? I mean, you had different, like the SMC dust and the LMC dust had different metallicities, and you had different models. Did you only use a single dust model overall for the entire galaxy? And if you included a different dust model intrinsically, could that, to adjust for, say, the differing metallicities, might have that changed your results regarding the dust-to-gas mass ratio?
Probably not very much, because the far-infrared emission is determined by the bulk of the dust mass, and you just care about the mass that's there. So it might have very much affected what we think the extinction curve is in those regions. So when we did our modeling for the Small Magellanic Cloud and the Large Magellanic Cloud, they were informed by having extinction curves. So it wasn't that we knew the metallicities of those galaxies was different, and therefore we wanted to do a new dust model. It's that we knew the extinction curve was different, and we knew we had to have a different size distribution. So if once when the day comes when we have extinction curves in different parts of Andromeda, then we could go back in there and bring this new information into the game.
Roseanne?
Well, this was just a comment which had nothing to do with exactly what you spoke about, but the connection to Cecilia Payne-Gaposchkin, because you mentioned at the beginning that it wasn't quite clear, but actually it turns out that when she first went to use a telescope, it was at one of the observatory nights, like we're going to have tonight, and quite unexpectedly she was left alone to point the telescope, which had been looking at a binary star, and her choice was Andromeda.
Good choice, I would say.
And that was how she met Sir Arthur Eddington, who played a big role in her career.
Thank you.
Well, I think we might be at our conclusion for the evening. Thank you very much. That's fantastic.